All right, welcome back. I think we'll have another short video for you this time too. I just want one last video kind of discussing these condensation reactions like the Enol condensation. And what we want to talk about is the Claisen condensation. Now, this is going to work almost exactly like the aldol condensation that we talked about, right? Except we're going to use an ester. Now, if we take this ester and we put it under basic conditions, right? If you notice that an ester is going to have some alpha hydrogens there also. And so we can come in, we can deprotonate those alpha hydrogens, and then two esters can come together. A couple of important things and a couple of different ideas here, okay? So first of all, right, let's talk a little bit about the basic construction here. We're going to need to have an ester wherein we've got at least two hydrogens there at the alpha position, okay? We're going to need to have at least two hydrogens there for this to come in and work, because we have to kick off water and we got to drive the reaction and all this kind of stuff, right? The other important thing is to recognize is that base. Now we can't use hydroxide. We can't use hydroxide in this case. Why? Well, if we try to, whoops, I almost gave away the answer there, right? If we took this and we put it under basic conditions, we would actually do the sapotification reaction, right? Remember, an ester under hydroxide, esters are higher than carboxylates are, right? So we would be driving a downhill reaction and make a carboxylate from our ester. That's our sapotification reaction, right? That's how we make soaps, right? You take a long chain triglycerides and you put them under basic conditions and you just basically boil away the water and you end up making soaps, right? That's our sapotification, how old-fashioned soaps were made, right? So you can't use hydroxide. But what can you use? Well, there's two bases you can use. You can use old reliable, right, for this chapter, which is LDA, a very bulky base that, doesn't come with the problems that sodium hydroxide will. Or, right, you can use the base of whatever here is in the ester chain, okay? Or that right there, okay? Because this can come in, attack the carbonyl, swing open the door, you close the door, you kick this off. But what do you replace this with? Well, you replace it with this, which could come in and attack and open and close the door and kick this off, which could come in and open the door, close the door. But eventually it's going to go after that hydrogen there, right? So the two bases you can choose are, you have to choose the conjugate, essentially the conjugate base of this alcohol that got added, right, or LDA. Either one's just fine. Why would you choose one over the other? Well, LDA, if you actually make it in the lab, right, you typically make it. You have to start with the amine, and then you deprotonate it with N-butyllithium, and you got to keep everything cold and all this kind of, right? So, maybe maybe the chemist is like me, and I'm just like, I don't feel like doing all that today, so I'll just add that into there, right? So, on paper, what does that affect? Nothing, right? Because LDA is shorter to write than that, right? So there's that. But anyway, what's the point here? What happens, okay? Well, we're going to end up deprotonating. Let me just clean this up. And then we can get through this mechanism here, right? So let's use our buddy LDA. Get this going, okay? All right. That's going to find another ester, okay? There's this. Okay, we should pause here and then go, right? So take a look. We swung open the door. We should always ask ourselves, nothing's changing, right? We're in a different chapter. I forgot what happened. Don't, right? We open the door. We're going to come back and we're going to close the door. And kick that off. Got it? So let me draw this a little bit differently here now, right? So that, in essence, is what we make after this closes the door and kicks that back off. In hindsight, I should have used different colors, but sorry. Apologies, but I think you guys get it, right? There's the part that we added, and there's the part that we started out with. So hopefully you guys are following along with that here. But we're not quite done yet, because look what we have here. An alpha position between two carbonyls. This is an extremely acidic hydrogen right there. pKa close to about 9, right? That's pretty darn acidic for an alkyl hydrogen. So what happens is this base is going to come back, right? And we end up doing an acid-base reaction. So really our product, after just the LDA step, is going to look like this. We have a minus charge there, and that's why we always come back and do a water workup or a weak acid workup at the end of it, right? So we can just do a little bit of H plus in there just to kind of get things finished up. Yes, that step is important, okay? This step is important. This does happen, and this actually can be very useful for us, okay? Because that is a very acidic hydrogen, and we can start to add things to that hydrogen, or excuse me, to that carbon, to that position by deprotonating that hydrogen there, okay? But this is our Claisen condensation, okay? Works with esters. We need to pay attention to what base we use, and we need to pay attention that we can close the door with an ester and kick off that base. This is, at the end of the day, one of the driving forces for this mechanism, that acid-base thing that happens along the way. That's why we need to have at least 2 hydrogens in that alpha position there for this to happen, okay? So now, again, you know, how do we deal with that in this course? I'm just pointing it out to you guys, right, as what happens, and understand that that is an important aspect of it, okay? But cool, there it is. So now we learned about ketones and aldehydes. They can condense together to form unsaturated, alpha-beta unsaturated ketones. We can bring together some esters to make some bigger groups. And if you'll notice, what we have now is a ketone and an ester, and we can start to do stuff with this ester and that position right here, and even that position over there at the end. So we start to add a lot of functionality into these groups, right? So we'll come back and talk about these just briefly a little bit later also, right? But the point being is that we can start to bring together some of these carbonyls, and at the end of the day, why these are so important is we end up making carbon-carbon bonds along the way. Forming carbon bonds, extremely important to do in organic chemistry, okay? But there we go. I promised you guys this would be a nice short one, so that's all I have to talk to you guys about now. I will see you guys next time.